So this is our next lecture, the density of states of the quantum wire structures. So here the diagram shown here, it's a quantum wire structure. Now we are going to use pen and paper. We are going to solve the density of states. We want to understand the detail of everything. So see the lectures, then hopefully you can understand the point. So the density of states in quantum wire, how we can calculate? Already we know what do you mean by the quantum wire. Suppose if the electron de Broglie wavelength is approximately equal to the dimension of the material, then electron is confining along the particular directions. Suppose if you are consider the three-dimensional material, the dimension in which the two dimension along the x direction as well as the y direction, the length of the material is, or the dimension of the material along x and y is matching with the suppose if you can call this is d, this is also d, this two dimension if it is matching with the de Broglie wavelength, then the electron is confined along these two direction, then it will be free the other third direction, because the third direction dimension is not matching with the de Broglie wavelength. That means electron can access all the energy in the along these particular directions, but it can't access all the energy here. It is having discrete energy spectrum. So that means electron is locked along these two directions. You can consider this is a two-dimensional spiral potential. So what would be the energy of the electron? Suppose if you are thinking the energy of the electron would be the En is equal to my electron. It's a quantum L structure. In one dimensional quantum L, you can call don't say it's the total energy of the electron. The energy of the electron is discrete along the x direction, because it can't move along the x direction. You got to need to solve the potential well problem for the x direction. That energy is Enx. Along the y direction, the energy of the electron is Eny, but in the z direction it is accessing all the energy. The energy of the electron in the z direction is equal to h square k z square divided by the 2 this is the mass of the electron. So the already we have the expression for the one dimensional potential. In general, En equal to the energy of the electron for the one dimensional potential, n square h square pi square divided by 2 L square. Here we need to solve the two-dimensional potential, the x as well as the y direction. That's why we have the separate energy, discrete energy for the x as well as the y directions. So here, suppose if you are having x, you got to put just x here, here y, because it's here also y, because the same set of equation we are going to use then the x as well as the y direction. If you did it, then you will get this same energy eigenvalue. So the energy, the total energy of the electron in the quantum wire is nothing but it's simply nx square h square pi square 2m L square plus along the y direction is ny square h square pi square 2m L square. Here we are calling this a thickness is d. If you are taking d is equal to L, then you will get this kind of energy eigenvalue. In the z direction, it is h square k square by 2m. You can call it kz square. So these energies are discrete energy. These energies are depend on the quantum number nx ny. This quantum number nx ny can have the value 1 2 3 up to infinity. It's having this kind of discrete energy. So you can say that energy is equal to, it's simply Enx, it's constant, plus Eny plus h square k square divided by 2m kz square. Or else you can just take this, you can write you can take, or you can write this Enx Eny like Enx comma Ny joining together. So h square k square by 2m, and this is a direction E. If I rearranging this one, you will get E minus Suppose I want to write it here. So rearranging this equation number 1, what you will get? E minus Enx comma Ny is equal to h cut square kz square divided by 2m. This is the energy of the electron in the quantum wire structure. You can take this equation number 2, but we need to calculate the in the quantum wire. It's the only one direction, it's continuous energy spectrum. That means it is accessing all the energy states in the only one direction. we 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 already have the if you are using the periodic boundary condition, the allowed energy states are, it shall be something like that. It's a discrete energy. The in between the two states, it's having then 2 pi pi L. This is a kz. These are the accessible states. Suppose if you want count then the number of electron allowed along this is a direction, it should be equal to the we want to do the same. Suppose take that some decay length. So you can call this is a decay length. Within this decay, how many electrons are allowed means, because we don't we may have the number of points. There are a lot of accessible state within this decay. We know what is the single accessible state, that length is 2 pi pi L. This is a decay length. If you are dividing this decay length divided by the smallest length, it will give the number of accessible state within decay. So what you have to do means, the number of electrons, just you need to calculate the number of electrons is equal to within this length, the number of electron within this decay, that should be equal to, just you got to do, you need to divide, this is the decay length, this is the smallest length. If you are dividing, it will give the number of accessible states within this decay. Each state is occupied by the 2 electrons, just you need to multiply by 2, or else you can simply rewrite the number of accessible states for the electron within the length decay, that should be equal to, you can cancel these two L pi pi, it's a simply decay. You can take, this is the equation number 1. So we have the number of electron within this the number of electrons within the decay length is equal to L pi pi into decay. We have the expression, take this is a equation number, you can call 1. We have the energy expression E minus, this is constant energy, discrete Nx Ny is equal to, simply you can call h square k square by 2m. But we want to rewrite the equation number 1 in terms of energy. What you got to do, you got to differentiate the equation, the energy equation. So if you are differentiating, this is d, this is 0 because this is a constant value, this is equal to h cut square by 2m constant, take it out. If you are differentiating this k square, it's a 2k dk. But in the equation number 1, we have dk only, so you can cancel this two. So what would happen? H cut square by m k into dk into de. Suppose we need only dk, keep it one side dk, push it everything other side. So the dk is equal to, what would happen? The decay equal to, if you are pushing everything this side, m divided by h cut square de by k. But we want to know what is the k, because we want to rewrite the equation number 1 and the everything in terms of the energy. Here we have in the denominator k, what we have to do. So just we want to write because from this equation you can write the E minus E nx ny is equal to you can keep it k square only other only one side, so the 2m divided by h cut square, it will push it that value to the left hand side, it will become 2m divided by h cut square. If you want k only, just take the square root on both sides, it will be 2m divided by h cut square root of e minus e nx comma ny whole power of. Now what we want to do, just we want to rewrite this equation number 1. What is your dk here? Substitute this k value here, substitute this k value in the dk. Just make sure what are the equation we need. This is the first equation we need, this is the second equation, you can call this as second equation. Substitute the k value into 2, therefore the dk is equal to m divided by h cut square dE by k value is simply 2m divided by h cut square root e minus e nx ny whole power of. Yes, it's right. Now what you have to do, now substitute the maybe you can simply simplify this one. If you want to simplify this one, this is m power 1 h power 1, here m power of h power of, so it will be simply, it will become square root of m by, okay, here it's a power 1, here it's a power of, so if you are going to push it up direction, it will be minus half. So then you have dE, here in denominator 2 it will be here, so 2h square e minus e nx ny whole power of, this is a dk. So this dk, just take this dk, substitute in the equation number 1. What we have in the equation number 1, it's the number of allowed electron in the decay length interval equal to L by 2 pi dk. So how, if you are substituting there, so that means we are converting this, the momentum in terms of energy. So what the value you will get means n of k ek, take the another page. So n of k dk, or the now you are converting within this energy, the number of electron is equal to L by pi square root of m by 2h square dE divided by square root of e minus e nx comma ny. So this is the density of states allowed for the electron. You can just make sure. Suppose within this energy interval, the number of electron is dE, so you can call this is the dN electron within this dE energy level. So this should be equal to L by 2 pi square root of m by 2 h cut square. Here we are nx and y are discrete energy level, so you need to put nx and y 1 1 or 1 2. That's a 1 1 means ground state, 1 2 you can randomly choose any number. That means all the accessible state, because electron is confined along x and y direction, it is having the discrete energy value along the two particular direction. So you got to put summation, that means nx comma ny, it will go on to infinity dE divided by square root of e minus e nx comma ny. We know the density of states, the expression, the g of e is equal to simply d dn by de. If you are rearranging the de, if you are pushing this side, that will be equal to L by pi square root of m divided by 2 h cut square sum over nx ny de square root of e minus e nx ey. This is, we push it other side, you can keep it 1 here. So this is the density of states of the electron in the quantum wire. Now we need to plot this one. How you got to do plot this one means simply you can do by this way. Draw the y-axis as a density axis. The x-axis you can take the energy of the electron. Whenever the energy is reaching the up to the energy E goes to, actually it will sudden shoot up when E is matching, because it's a denominator, square root of denominator. If it is 0, then it will be goes to infinity in reality, but it is not actually infinity in the realistic case, because the number of electron is fixed. It's looking like a density will be maximum. It will suppose whenever the E, Nx, Ny, it is matching, energy is matching with the allowed value. Suppose E is equal to E11, Nx1, Ny1. If it is matching, it will be square root of 0. It will be looking like infinity, but it's not infinity. It will be sudden shooter at the E equal to Nx, Ny. Then it will go like a square root function of energy. At next energy level, what would happen? Again, it will be sudden shoot up. Then it goes to the next excited state. After next exit, it will go to sudden shoot up. Then the density of states will be looking like that. Each nx and y value, it will be, you can see the sudden shoot up. After that, it will decrease as a square root function. The density of states decreases as a square root function after some energy next to E. And suppose you can call this as a E11 ground state energy. This is the first excited energy. This is a second excited state energy. Like that, you can plot it. Each excited state, it will sudden, you can see the sudden shoot up in the density of states. Then after that, it will go as a square root function. So this is the density of states, our picture for the quantum quantum wave structure. We derived everything, the density of states for the electron in the 1D quantum wire. Now we are drawing the density of, here the diagram shown here, it's a actual diagram plotted using the computer software, the energy versus the density of states. Hopefully you can understand why it is sudden jump at a particular discrete energy level. Then after it is discreting, it's not exponentially decreasing, it is like a square root function of discreting as of density of states as a function of energy.